Ta-da! 4:30. Man, that's loud. Somebody really doesn't have much of a voice, needed amplification. Okay, so we're going to finish up improper integrals. These are integrals where either the function becomes unbounded or the limit of integration becomes unbounded. And we're only going to do the unbounded integration limits because they show up in Laplace transforms and probability quite a bit. So that's the most important ones. And whether it's the upper limit going to infinity or the lower limit going to minus infinity is completely irrelevant because you can just flip those. So we'll just look at the upper limit going to infinity. And with any limit, it can exist and be finite. It can exist and head to plus or minus infinity, or it simply doesn't exist. And when the limit doesn't exist, in the case of an improper integral, we also say it's undefined. So you can say does not exist, or you can say undefined. By using the power rule, we've got families of functions where it's easy to check whether, when you use them as the integrand in an improper integral, do you get something finite or not? And in fact, there's a line of demarcation when you look at these types of functions. If you just do 1 over x, its antiderivative is the natural logarithm, and the natural logarithm grows unbounded. So the area under 1 over x from 1 to infinity is unbounded. So it's a divergent improper integral. And then you can take 1 over x to the p where p is not equal to 1, because we just did the case p equals 1, which got us the natural log. And there the key thing to come away with is it's finite if p is strictly bigger than 1, and it's infinite otherwise. I mean, you can even consider p negative, but if p is negative, you got 1 over x to the p is x to the minus p, and p is negative, it's a monomial, and so x cubed, yeah, that's going to have infinite area. So it doesn't really matter. So it's really p between 0 and 1 infinite, and p bigger than 1 finite. And in particular, 1 over x squared, if you just plug everything in, its area is 1 when you integrate from 1 to infinity. Okay, so those are just fairly elementary limits and elementary antiderivatives. And in theory, it doesn't look very powerful, but we're going to use it in the comparison principle. And then the power of knowing this class of functions becomes much more relevant. So we're going to consider two functions. We're going to compare one to the other. So a function f defined on some unbounded interval. Its friend g, also defined on the same interval. And we'll assume that they're both piecewise continuous. And the reason we want to do that is that if we take any bounded interval, their Riemann integral will exist. So the Riemann integral exists and is finite. on AB for B finite. Okay, so that's where the piecewise continuity comes in. If you want to assume it's continuous, that's fine. You want to assume it's differentiable, that's fine. Those are all piecewise continuous functions. In addition, we assume that 0 is less than f of x is upper bounded by g of x for all x bigger than or equal to a. So for all x between a and infinity. Okay, so I'm just going to do one of my probably now infamous drawings. A doesn't have to be positive, but I'll put it on the right-hand side of the limit, and then I'll draw a function f of x. I'm just going to make it continuous. It has to be bigger than or equal to 0. It doesn't have to be monotonic or anything. But I'm going to draw it in such a way that you might believe its area is finite, okay? So this keeps going all the way to infinity. And then another function, g of x. Who knows where it starts? It's greater than or equal to f of x, so it could touch f of x. And we'll give it a shot where it could be, have finite area, it might not. Okay, so this is g of x, and this is f of x. 0 less than or equal to f of x less than or equal to g of x. And I didn't put any points of discontinuity or anything in them because it doesn't really matter to the argument. So here is the comparison principle. However you want to define it, the area bounded by f is certainly less than or equal to the area bounded by g. Hence, if the integral from 0 to infinity of g of x is finite, then f of x is finite. Integral 0 to infinity g of x dx finite. Well, if that one's finite and it upper bounds f, then the other one has to be finite. And then conversely, if f of x is like 1 over x, so its antiderivative is log and the area underneath it is unbounded, well, so if the area under f is unbounded, the area under g is unbounded as well because g is bigger than or equal to. So integral 0 to infinity f of x dx equals infinity. So it's that integral is divergent. It implies the other one is divergent as well. So that is the comparison principle in a nutshell. You could write theorem above it and everything, and the proof is the picture. There's nothing more to do. Okay, so for every finite b, the integral from a to b of f is less than or equal to the integral from a to b, and then you just take the limit as b goes to infinity, and you get these two conclusions. So on the surface, it looks kind of tame and not so applicable. Well, let's just show that it's pretty powerful, okay? So we often call the following test functions. It's not a universally adopted name, but we were just talking about these power law guys. And it's unbounded if p is less than or equal to 1, and it's finite if p is bigger than 1. And why do we call them test functions? It's because we can often use these guys to bound f. So we put it here, and we get that to be finite with, say, p equals 1.3. Then we get f finite, or conversely, we bound it the other way, and we have p equals, say, a half, and we get infinity, and that implies this other one is infinity as well. So that's where the word test function comes in. And I think this one example will set everything straight. Determine whether the integral from 1 to infinity x cubed plus 4 x to the 5th minus 3x plus 21 dx is convergent or divergent. Okay, so that's the problem. Okay, so in my comparison theorem, I mentioned the word piecewise continuous. When do these functions that are ratios of polynomials, when do they become not continuous? Yeah, if between the limits of integration, the denominator vanishes and the numerator's not doing the same, so we got some sort of nice limit thing, you're absolutely right. So, yeah, so we need to worry about where the denominator vanishes. So we'd have to calculate roots, and I did that. I just went to my favorite LLM, and I said, hey, what are the roots? And there's a real root at minus 1.93 plus or minus 0.001, and 4 complex roots. Okay, so this thing has 5 roots. 4 of them are complex, so there's no real value of x causing it, except for this one, and that's at roughly -2, and -2 is not between 1 and infinity, okay? So we get to conclude the integrand is continuous on 1 infinity. Okay, so that's nice. X cubed over x to the 5th, etc. There's no discontinuities. Okay, so how do you think about these types of problems? Look, we're worried about x's getting large. From 1 to 10,000, that's a finite interval. Everything is finite, okay? What happens when x gets big? Well, x cubed divided by x to the 5th is approximately 1 over x squared, right? So f of x equal to x cubed plus x to the 4th over x to the 5th minus 3x plus 21 is approximately 1 over x squared for x large. Okay. And we know that the integral from 1 to infinity of 1 over x squared is finite, so hence it all should work out. That's the intuition. So it should work. So it should be convergent. Our integrand. That's the intuition. Okay, so just make sure that we mean f, the integral, 1 to infinity dx. That's what we mean by it. It should be convergent. Okay, so now the question is, how can we use this idea? Whoops. Okay, we've got an idea. We see what the function's long-term behavior looks like. We know those functions play nicely with unbounded integrals. How can we use that to show that the original function is actually convergent? Okay, any questions on the thought process, what we're trying to do? Okay. Okay, so maybe the only mystery is how do we put all the details together so it's not just, yeah, this one seems good. Okay, we're good. We're moving on to the next one. Okay, so we're trying to avoid doing that. Well, so let's divide the numerator and denominator by the highest term, which was x to the 5th. So we can take our our function. So it had x cubed in the denominator divided by x to the 5th is 1 over x squared. And it has 4, in the numerator, and 4 in the numerator, divide that by x to the 5th. So those guys look good. Okay, so those are all of the form 1 over x to the p, where p is strictly bigger than 1. So I don't see any problems there. And then the x to the 5th term divided by x to the 5th, that becomes 1. And then we have minus 3, 1 over x to the 4, and then 21 over x to the 5th. So that's the function we have to deal with. It's a rational function, so this will be d of x. So the numerator's in a nice form. What I want to do now is find an upper bound for f of x, which only has these simple terms like that. So this is still problematic when we do the integral. Now, putting this in red, so I want to upper bound f of x by something that I know is convergent. The numerator is already in a really nice form. I don't need to do anything to it, but if I put an upper bound for the numerator, that would certainly upper bound f, but I don't really need to do it. It's already nice. Now, to upper bound f, the other way to do it, you grow n or you shrink d, right? It's obvious. 1/3 is less than 1/2, so you shrink the denominator, you get a bigger function. I know you guys know that, so we need a lower bound for the denominator. Okay, like replacing 3 with 2 gives us an upper bound. Okay, so we shrink d of x, and that's the hard part in this thing, okay? So make sure I get my numbers right. So let's write out the denominator. It's 1 minus 3 over x to the 4 plus 21 over x to the 5th. Okay, so I want to shrink this. I want to find something smaller than d of x that's nice. Well, for all x bigger than or equal to 1, our interval of integration is from 1 to infinity. This is positive, so if I throw it away, that's certainly true because this is positive. So dropping it is not going to increase, it's going to decrease. Now I'd like to remove the 3 over x to the 4 and have my lower bound be a constant. Why would I like that? Because if I can replace all of this with a constant, then I've got 2 trivial integrals to do. One over a power rule and another power rule. This just becomes a constant and life is easy for me. So can I do that? So this is non-obvious until you've done a few of them. Okay, when x becomes really big, 1,000,000, 3 over 1,000,000 to power 4 is like minuscule, and so this is really, really close to 1. So I could do a lot tighter bounds. I could just do x bigger than or equal to 2 or something, but making this 10 makes this a super easy quantity to understand. So that's 3 times 10 to the minus 4. And so this is greater than or equal to 0.99. Okay, so 0.99 is my lower bound, and it holds for x greater than or equal to 10. Now, is that useful? So let's return to the scene of the crime. 1 to infinity. Yes, let's just write it all out. That was, I don't even remember what it was anymore. X cubed plus 4. X to the 5th minus 3x plus 21 dx. Okay, so I'm going to write this as the integral from 1 to 10. Plus the integral from 10 to infinity. Okay, you guys know what goes there. Go ahead and copy it while I make my things on the same level. This is 10 to infinity. Then this stays 1 to 10. And then I replace this and that was 1 over x squared plus 4 over x to the 5th. Okay, the key thing is this part that I didn't bound, I don't care. This is continuous, so finite. Finite by continuity, and this being a bounded interval. And this is finite by 1 over x to the p for p strictly bigger than 1. So the 1 over x squared, that's finite, and the 4 over x to the 5th, that's also finite. And so, conclusion, it's a convergent integral. Okay, so did this process ring any maybe unpleasant bells back early in the course when we were looking at limits at infinity? It should have, because we essentially did the same thing by finding bounds for rational functions and then looking at limits of individual terms and understanding what was happening that way. And when we did that, we formed we gave ourselves a value of epsilon, and we found the actual value of n to make the limit within epsilon of the final value L. And then we moved on to limits the easy way, okay? So we had, I would call this bounding and determining it the hard way, because we went in and we did all the bounds. But once you see how these bounds work, I think you can see what's going on. Okay, so let's take a rational function and let the area C infinity be such that f of x is continuous. So that just means we have C is bigger than the largest real root of the denominator. So you calculate the denominator, it might have a root at plus 46, okay? So we take C to be 46.1. So now the function is continuous. We can do the same bounding tricks to divide by x to the n and everything. And at the same time, just like we did with limits, we can throw in these exponential terms. And so we now have just entire families of convergent and divergent improper integrals. We don't really care how fast or slow the rational term grows, because if we have a positive exponential, that's going to dominate, and this thing is going to be divergent. This will say whether it's plus infinity or minus infinity, but that's all. Same thing here, if we have a decaying exponential term, we don't really care about the relative size of the numerator and denominator. It will still be convergent. And then if we're back in the case that we just analyzed, as you guys can guess, if the denominator is at least twice bigger than the numerator in terms of the degree, then when you do all those bounds, the worst you end up with is 1 over x squared. You may get 1 over x to the 4th or 5th, like we also had in ours. But if m is a cubic and n is a quartic, you ultimately end up with a 1 over x, and 1 over x is the natural log, and that's divergent. Okay, so you get necessary and sufficient tests. So this is the easy way of doing improper integrals. And it's strictly analogous to how we had the easy way of doing limits at infinity. And those are two different things. Make sense? Too much sense? Okay. So let's see if you guys have this down. Here's the first example. Integral 0 to infinity x plus 1 over x to the 24 plus 1 dx. Convergent or divergent? B. Integral 0 to infinity x plus 1 x to the 24 minus 1 dx. reminds you of the horrors of Math 116. Don't associate that with me, please. Thanks for your comment, Jason. So anyway, online, inline, offline, out of line, all of you. First one, is that improper integral going to be finite, unbounded, or it simply doesn't exist? What's slowing you down? I know what's slowing you down. You just want to get to ODEs, and so do I. Ha, 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 ha. Look, between 0 and infinity, this thing has no roots. It's always bigger than 0, so no roots. So the function is continuous. The degree is 1, the degree is 24. So I think there's a difference of at least 2 there. Okay, so this is convergent. Okay, B. The second one, okay. This vanishes at what value of x? 1. I made it easy, okay? Is 1 between 0 and infinity? Yes. Okay, so then the answer is the above result does not apply. Because x to the 24 minus 1 equals 0. Has a root at x equals plus 1, and 0 is less than plus 1 is less than infinity. Okay. So now, if we change the lower limit to 5 or something, you're going to be good. Okay, so then everything would work. Because for 6 and higher, clearly x to the 24 is so much bigger than 1, it can never vanish. Okay, so 2 will work as well. So if you change the lower limit to just being strictly bigger than 1, 1.1, everything will be fine. Okay. So what if your function takes on both positive and negative values? So let's go back and look at our motivating picture for the comparison principle. Both functions here were non-negative. So what can we do to give us a little bit more freedom? Okay? So definition piecewise continuous function. So we just threw in the piecewise continuity because it's the most general class of functions we know how to do Riemann integration for. Continuous function is absolutely integrable. If the integral from a to infinity of absolute value of f of x dx is finite. So let me draw a function that does both. And okay, so absolute value of f of x So here's the main thing that you want to know. Proposition. If f is absolutely integrable, then f of x dx, no absolute value sign, right? So then that improper integral exists and is finite. Okay, so what this says, if your function is taking on both sides, look at its absolute value, and then you can apply the comparison test to the absolute value, and then you get facts about the original function. Okay. And why it's true is fairly intuitively obvious. It's because the area under the absolute value is all of the positive areas added up, and then all of the negative areas added up. So that means the positive part of the function gives something finite. If you just looked at where the function is negative and add those up, they're going to be finite, so their sum is finite. Okay, so it's not hard to prove, but it's just a really useful fact. And the most common application of the above, so of absolute integrability, is to f of t equals t to power k, what did I call that? E to the at, sine or cosine omega t. Okay, so you guys don't know this yet. The solution of all linear differential equations consists of sums of terms that look like this. So are those nice things? Are those bad things? If you try to integrate those solutions, are they convergent? Are they divergent? Well, you can analyze it quite easily because the absolute value of f of t, when t is positive, this is already positive, this is already positive, and you just need to take absolute value there, and that's less than or equal to t to the k e to the tk, because sine of x is less than or equal to 1. And when you integrate something like this, well, it's a special case of these guys. And what you need is the exponential to be negative, and then it dominates whatever monomial rational function is there. And if the exponential is positive, even if that's 1 over t to the 1 billion, it doesn't matter. The exponential dominates, and it's divergent, etc. Okay, so that's why knowing something about this. And yeah, so these will pop up when we do solutions of linear differential equations, without the absolute value, these functions. And the only last thing to do here, before we take our break and start ODEs as promised, is one little warning. Okay. Slide down, please. Okay. So we were doing limits when either the upper limit goes to infinity, we could have turned it around, kept the upper limit finite, and let the lower limit go to minus infinity. You sometimes come across integrals where both of them go to infinity. So, what you never ever want to do, this is just a warning, never ever write this limit as the limit as c goes to infinity of minus c to c. And the reason you don't want to do that is shown in this picture. Come on, be nice, shrink down. Because if you just take x, and you integrate it from 0 to infinity, obviously x squared over 2, blah, 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 that goes to infinity. If you just went the other way, it goes to minus infinity. But if you take a symmetric limit from minus c to c, that's always 0. And the limit is going to be 0, and you're going to say, this makes sense when what you're doing is taking plus infinity and minus infinity and adding them together, and that's a no-no. So that's the only thing. That's the only thing we have to be careful about. Okay, so we'll stop there. So we'll take our break. And Max, you got good snacks and stuff for people? Okay, I'm going to get everything fixed. download a QR code. Okay, differential equation. So we said a differential equation is an equation, has an equal sign in it, and it has a derivative. But what makes it ordinary? I mean, you guys want to be solving extraordinary differential equations. You don't want to be dealing with ordinary differential equations, right? Okay. These are ordinary differential equations. Things that look like x dot of t plus 3x of t equals sine of t d2x dt squared plus, I don't know, 11 sine of x of t equals 0. Okay, the key thing is that there's a derivative with respect to a single variable. And that'll make more sense when I show one that has more than one variable and you go, oh, now I get it. But these all have derivatives with respect to t. And that 11 almost looks like a norm, so let's make it 14, okay? So it's not a norm. So the ordinary means there's only derivative with respect to a single variable. This is a partial differential equation. You've got something like U is heat flux, and this is its time rate of change. And then it's proportional to the second spatial derivative. So x is like distance along a bar. T is the temperature at time. So this is called the heat equation. We don't care. We're not solving it. But the key thing is there are derivatives with respect to time and space. When I mean space, I mean R1, R2, R3, R4, and that was x. So there's two derivatives. And if I just went up to the previous one and instead of writing d's, I wrote partials, but it's still only partial t second derivative, all that is fake news, okay? That's just fake news because you really just have a single derivative, okay? So the key thing is two or more derivatives. Or variables being differentiated. Okay, so that's a partial differential equation, and we stick to ordinary, okay? It's hard enough. So that's us. So I had some videos that I think are just kind of semi-fun. this is a 3-link mechanism on a cart. Okay, so the thing that's moving, the blue thing is moving back and forth, and it's providing energy. That's the only place that there's a motor. So there's really 2 big motors at the end pulling a cable really, really fast. And they got the motors offloaded from the blue box so that the blue box is lightweight and can move quickly, okay? That's all it is. And then there's 3 links attached to it. What looks like motors there, you know, kind of looks like a motor or something here. Those are just, that's an encoder, and that's a mass. Okay? So that's feedback control to balance it. And they're using optimization to find trajectories that allows it to go from dangling to upright in the least amount of energy. And they're showing you all of the various equilibrium points that you can have. So you can have 1 up, 2 down, 2 up, 1 down, 1 up, 1 down, 1 up. All those things are possible. And they found solutions for all of them, okay? So it's just kind of like, whoa, dude, you did your homework. So we've been deriving Lagrangians for 2-link, 3-link mechanisms. So we know how to get those differential equations, and we know they're fairly complicated. And our base was fixed. Now we could add a moving base. This just came out. The sound is not important. But if you get bored with legs and you're bored with wheels, you put wheels on legs, okay? So that's the next thing. And you've seen that in the quadrupedal space. So what describes the motion of that object? Differential equations. And they can be derived using the Lagrangian mechanics that we went through. Now, this is clearly not point masses, so you would need to use moment of inertia and center of mass and be a little bit more complicated. And it's not planar, it's 3D. So that means you want to take Rob 298 to robot dynamics with Gillespie and Fazeli, okay? But that's how that stuff works. Pretty impressive, isn't it? Yeah, well. Anybody here has a start on project 2 yet? Start? No? Little tiny, maybe, sort of, don't really want to get into it. So this is code that is, it's all available to you, but this part of the code is not in your boxes in the Jupyter notebook. There's little commands that say include, and it brings in a set of utilities, okay? Can you recognize the big D times Q double dot plus C dq, et cetera, as the robot equations? Yep. Okay. They're being implemented as equality constraints because differential equations are just equations. They are things that have an equal sign in them, okay? So, nonlinear constraints, I've got air resistance in there. This first part, all it's doing is saying that the accelerations that are being used as optimization variables have to satisfy the equations. And then there's another constraint that's doing trapezoidal integration. So you guys are going to be doing optimization for the following objects. It's super cool. Come on. Don't be so big. You're taking up all my space. Yeah. So this is a tumbler. You're looking at, I don't think it's a tumbler. Well, yeah, it is. You see the X and Y, they're free. Okay? So the X and Y can move and the theta can rotate. So what you guys are going to be doing in project 1 is you are finding initial conditions for jumping off the mat to do a loop and then land on your feet, okay? Landing on your feet, that's an equality constraint. Okay, you're setting the initial velocity as you jump off of the mat. The position is fixed for you, and then you're supposed to land over here. Now, in the background, there's a differential equation that's being solved to go from the initial velocity, just like you were shooting a basketball. There's F equals ma being solved to see if it goes through the hoop or not. So in jump, all those are being solved in the background. You're not, because we haven't covered differential equations yet, but they're there. And there's another one for a 10-meter platform diver. And it's even cooler because it's 2 links. Well, I guess this is my second rigid link. And you jump off, and then you fold, and you tumble, and then you have to land. You have to stick the landing, okay? And it's another set of robot equations, but it's the same. So you guys are using optimization to find solutions of differential equations. So we're going to go through some stuff, and I'll define what a solution means. But that's what all the big boys do, is they use optimization. So all the work I did on bipedal locomotion, optimization, because we want to minimize the amount of battery power being drawn to do a certain type of gait. We want it to be robust to certain types of perturbations. But Boston Dynamics is doing that. Unitree with their amazing humanoids, if you've been following what it's doing, they're all using optimizations. You guys are doing the same thing that the big guys and the big gals are doing, okay? Now, what we're going to do is go through and see how you solve differential equations by hand, okay? And just get solutions, not optimal solutions. They are solutions. But what you guys are doing is really how I use differential equations. I put them in an optimization package, and I tune the parameters, the inputs, et cetera, to get the desired behavior. So it's pretty fun. Now, what we're going to do is pretty cool, too, because we're going to do something very physical. We're going to study parachutes. So you guys are too young to have seen, at least on TV, but you've seen videos of it, the space shuttle landing. Okay, so that thing weighs 2,000 tons. Okay. Doesn't matter whether it's metric tons or other, because they just differ by 10%. Okay, so it's 2,200 British tons or 2,000 metric tons. Who cares? That's a lot of tons, okay? If you just turned on the brakes, you would melt them in about 30 seconds, okay? And then the wheels catch on fire and this thing falls to the ground. So what they do is they trail a huge parachute. It's a drag chute that slows it down to about 30 miles an hour, and then they can just use the brakes to finish it up. Okay, so we're going to analyze that. We're going to analyze it with a linear drag model and a nonlinear drag model. And then we're going to do a parachutist. So falling through the air. And, looking at these, you would say, space shuttle's got to be a lot more complicated than a parachute, just a little goofy hippopotamus falling through the sky. And you'll see that that's not the case, okay? So, but that's what we're going to do. So we're going to do 4 models, 2 of each, linear drag and nonlinear drag for each of them. So we're going to derive the differential equations and solve them and define what is a solution, etc. And so the first one is linear drag for the space shuttle. Are you anxious to see how it's going to work out? It's kind of cool, isn't it? Yeah, okay. So here it is. MA equals F. So that's equivalent to M. I'm going to write it as V dot to start with. Okay, acceleration is the time derivative of velocity. And I'll put the time variable in there. So F equals ma, that's Newton. I just rewrote it so that the derivative is on the left side, which is more traditional. Then I'm going to do linear drag. That means F of t is minus some constant V of t. That's supposed to be a kappa. So let me see if I can make a better kappa. Who cares? If you want to call it K, we don't care. Okay. So here's the differential equation then. V dot equals minus kappa over m. So I'm dividing by the mass on both sides times V of t. So that's the differential equation. Now, when the space shuttle touches down, it has an initial velocity. So we need to specify that. Okay? So, and you may reset your clock to 0 exactly when the space shuttle touches down, or you may still be running the clock from when it entered the atmosphere, okay? So that's why I'm putting T0, not 0 there. Who knows what clock you are using, okay? So this is called an initial condition. This is the thing that you guys are optimizing in the first part of Project 2. We will see that the solution, the time function V of t that satisfies the derivative relations here on the left and the initial condition depends upon the initial condition, and you guys are choosing the initial condition to get nice behaviors out. That's what you're doing. Okay. Claim. When you have this physics, the solution is V0 e to minus kappa over m times t minus t0. T greater than t0 is a solution of the differential equation. Okay, so I'm going to write it formally like this in the beginning, and then we'll be less formal once we kind of know what's going on. And we haven't used the proof word in a while. But I'm going to write the proof that this is a solution in a way that lets you know what a solution is. So the proof, the first part, V of t satisfies the initial condition. Okay, so we have an equation, but we actually have two of them. We have this equation, and we have this equation. The one on the right here is setting the initial condition, and this is telling it how the velocity, so the acceleration, and the velocity are related throughout time. So the first thing we need to do is, does the v of t that I gave you satisfy the initial condition? I don't know. Let's plug in the initial condition and see what we get. So if v of t is that function, then v of t0, that's just v0 e to the minus kappa over m t0 minus t0 and t0 minus t0 is 0, e to the 0 is 1, so we get v0 e to the 0 equals v0. So yep, satisfies the initial condition. Okay? So that's the first thing that a time function must do if it's going to be a solution to the differential equation. If it doesn't satisfy the initial condition, it's not a solution, because there's two conditions. B. V of t satisfies the ODE. Well, so what does that mean? That means I have a time function, so I can plug it into here. I need to compute its derivative, plug it into there, and then check that that's true. That's all it means. Okay? Well, oops, I guess I'm changing colors. V dot of t. Well, we know how to differentiate exponentials. And then we have to differentiate what's up there. And that'll be minus kappa over m, because we're differentiating with respect to t. This is a constant that goes away, and the coefficient of t is what we have here. So this equals minus kappa over m v0 e to the minus kappa over m t minus t0. This is v of t, and so we get equals minus kappa over m v of t, and that's the differential equation. Okay? Recall the ODE. It was v dot of t equals minus kappa over m v of t. And so we calculated v dot, did a little tiny bit of algebraic manipulation, and bingo, it satisfies the ODE. So it is a solution. Okay, it will turn out that it is the only solution, so it is the solution, but we don't know that yet, so we'll just say it is a solution. So if I have a differential equation, if I can find a time domain function where I fix the initial time, I get the initial value, and I do all the required derivatives. I think I had one up here with 2 derivatives, right? So here, I would have to have an x of t, and I'd have to differentiate it twice, and I'd have to show that that is equal to minus 14 times sine of x of t to show that it satisfies the differential equation. And for these, I did not specify initial conditions. Okay, so left-hand side equals right-hand side. Now, what you're probably curious about is how to actually find that solution if somebody doesn't give it to you. Okay, and we're going to use a method called the separation of variables. So it works a surprising amount of the time, in my humble opinion, but anyway, we'll see that it certainly can't solve all problems, but it's a good way to get started. Okay, so I'm going to write the differential equation using Leibniz notation. And there's a method to the madness here. So there's my differential equation, dv dt, not v dot this time. Okay. The first thing I'm going to do is to replace the dummy variable t by tau. It seems totally unmotivated at the moment, I understand. But its wisdom will become clear in just a second. So this is now dv of tau d tau equals minus kappa over m v of tau. Whoops, I said tau and I wrote t. Now I'm going to drop the explicit dependence. Okay. And what I mean by that, I just want to write this as a differential, an increment in v divided by an increment in my new time variable equals minus kappa over m times v. So I don't want to muddy the waters with that dummy variable. Okay, I'm dragging this out, I know, but I want you to be able to do it on your own. So here we have v's and taus on the same side, so they're mixed. I want to separate them. Here it's simple, we only have v's. So I'm going to get all the v's on one side and all the taus on another. Okay, oops. And this is the separation of variables. Separate variables to each side. Well, If I do that, I can have dv over v equals minus, this is just a constant, kappa over m times d tau. Everybody see why having v dot would not have been a very good move, okay? Because you don't have two parts to it. You don't have the increments, the ratios, okay? But that's fundamentally what derivatives are about, as you saw in that Mathologer video where we learned how to derive the chain rule, the product rule, and you guys did the quotient rule, okay? So this notation can be quite nice. Now we're going to integrate both sides. Okay, so I'm going to write out the integrals. And now I'm going to show you why I got rid of the time variables, okay? Remember, we have this thing called the initial condition. So we really want to solve this equation from tau starts at t0 and goes all the way up to t. And that means v goes from its time is at its initial value, so v goes from its initial value up to v of t. And I'll just remind us that that's just a constant, okay? So that's why I got rid of the, I changed the dummy variable because I didn't want a t here and a t here, okay? So t is our variable that we're using to get the solution. Well, now it's just kind of, it's almost algebra, right? We know the antiderivative here, so we get natural log of v evaluated from v0 to v of t equals minus kappa over m, and the antiderivative of 1 is tau, and it's evaluated from t0 to t. So I guess I can do the if and only ifs here. So now the rest of this is just grungy algebra. We've done the calculus. So the calculus was our differential equation, separating variables, applying antiderivatives, and now we just have to evaluate them. And that's really tedious. So the log of v of t minus the natural log of v0 equals minus kappa over m times t minus t0. Logarithm rules says that's v of t divided by v0. Once again, this is just grungy, messy algebra, the part of calculus that at least I hate. I don't know if you guys hate that part of calculus, but I hate that part of calculus. Okay? And so how do we get rid of the logarithm? We take the exponential on both sides, okay? And so we get v of t over v0 equals e to the minus kappa over m times t minus t0. And then we did it. We multiply both sides by v0, and we get the function that I told you was the answer, and we proved was the answer. Wow. Okay, separation of variables. We start with the ODE, write it down in friendly symbols, turn it into an antiderivative problem, and then do the algebra. And then we found a solution to the differential equation. And once again, how do we know that all that manipulation was a solution? That's why we did this first. We checked the initial condition, and we checked that V dot and V are related by the differential equation. So that's it. Seem doable? Okay, so that's the space shuttle with linear drag. 2, space shuttle with nonlinear drag. Okay. M v dot of t equals f of t. F equals ma. V of t0 equals v0. So Newton's laws. We're still applying Newton's laws. What are we changing? We're changing how the force of the air resistance from the chute is computed. Okay, so now it's proportional to the velocity squared instead of velocity to the first power. And our differential equation becomes mv dot of t equals minus kappa v squared of t, v of t0 equals v0. Here's the solution. Once again, we're going to find it, okay? But it's got a constant v0, the initial velocity in the numerator, and then 1 plus v0 times t minus t0 times kappa over m. So if we plug in t0, this goes away and we get v0 over 1. So it satisfies the initial condition. At home, you differentiate it and you plug it in, okay? That's just routine. Okay, I think the more interesting part for us is, where does that come from? Okay, it's a pretty funky formula. V0 over 1 plus V0. If you want to move all the constants up front, then T minus T0, okay? Now, you can compute the solution once again by separation of variables. So I'm going to just recopy the ODE. M v dot equals minus kappa v squared Okay, so that's the ODE, and I dropped the T's, but. Okay, so we're going to write this as M dv d tau. We're going to go straight to the changing the dummy variable. In fact, I'm going to get rid of the M right away and get it over here. Okay. So I just replace v dot with dv by d tau, my new dummy variable. Move the m to the right-hand side, so I've got a constant in front of v squared. So I do the same thing as before, except this time, instead of dividing by v, I'm dividing by v squared. And once you've done 8 or 9 of these, which I hope you never get to that high in your life, I'll be honest with you. So now we're going to integrate both sides and try to apply antiderivatives. So this is going to go from the initial time to v of t, and we've got 1 over v squared dv. And this goes from initial time to t. I didn't bring it out this time, but I could have. So I'm not putting all the if and only ifs in between. I think you see the logic now. And that's not a minus, that's just part of this. So v to the minus 2 becomes v to the minus 1 divided by minus 1 from v0 to v of t. And then this equals minus kappa over m. And then it's tau evaluated t0 to t. Everybody good with the power rule there? V to the minus 2, you increase it by 1, and then you divide by the power. Yay! And then so you can do the algebra if you want. Okay? So you just got to plug in v of t, the v0, the t, and the t0, do the algebraic manipulation, and you get this answer here when you're done. Okay? So that's just algebra. You can do that at home. And if you guys are happy with that, I think I'd suggest that we call it a day for derivatives. We've introduced the idea of ordinary versus partial differential equations, and we've agreed that having one derivative in the equation is enough. We've taken 2 interesting situations, the space shuttle, and we did it with linear drag and nonlinear drag. And in each case, we could derive a closed form solution to the equation. So we've actually solved differential equations officially. You guys are doing them unofficially because you don't know what a differential equation is while you're working project 2, pretend. But you're actually solving differential equations using optimization, which is really, really important in robotics and all fields of engineering these days, okay? So here I'm showing you how you get little bitty equations you can manipulate and get closed form answers. We'll continue with that when we do our little hippo coming down in the parachute. We'll do linear and nonlinear drag for it. And then we'll move on to more conceptual notions in the theory of differential equations. But they describe physical things that mean, that are important to us. And we'll leave it at that. Thank you.